This is premise for number 65, and today we're talking about how damaged rotor blades affect the aerodynamic characteristics of the turbine. And to do that, we're going to be looking at a paper called Effects of Leading Edge Modifications in Damaged Rotor Blades on Aerodynamic Characteristics of High Pressure Gas Turbines. And the link in the description can be found. It's open access, so you can find it yourself if you like, or you can listen to the podcast or follow along on YouTube. So in turbines, it's not uncommon for the blades to get damaged, and that can reduce the lifespan of them. And they also affect these damaged parts also affect the aerodynamic performance and the heat transfer performance of them. So it's important to understand how these damaged parts affect the performance. So they start off saying to enhance the power and efficiency of a combined cycle power plant. So a regular, let's say, just a turbine, the turbine inlet temperature is usually increased, and that's true. So one thing that is quite easy to do is to get a general idea as to how efficient a turbine is simply by understanding what the temperature difference is across the blades across the entire thing. And the reason why you can do that is because by understanding what the temperature difference is, you can understand how the energy changes across. So if you treat the gas, for example, as a ideal gas, that's the easiest way to do it. You then can look up the enthalpy values of the ideal gas or calculate them very easily. The enthalpy is a measure of how much energy the gas has at a certain temperature. And so if you understand what the enthalpy is at the start compared to at the end, you can determine how much energy has been extracted. And then you can figure out, well, how efficient this turbine is operating. So the higher that difference, the better the turbine is operating, generally speaking. And now there are other factors you need to consider. For example, if you take out too much energy, then that can affect the upstream conditions where you're feeding flow into the turbine. But that's getting into fairly complicated issues in terms of just the turbine itself. Increasing that temperature difference is the way to increase its efficiency and its power as well. So the turbine inlet temperature is strongly affected by the outflow and the temperature distribution of the combustor. And what these two things do, they can create things called hot streaks. And hot streaks are non-uniformities in the temperature distribution inside the turbine. So what that means is you can get certain regions which are much hotter than other regions, which then reduces the lifespan of the turbine because these hot regions, they like heat concentrated regions, and heat concentration kind of is like stress concentration where you just keep pummeling this area with with greater heat, and that wears it out quicker. So that can lead to failure much more quickly. So the conditions of hot streak operation are similar to the actual operation conditions of gas turbines. Hence, it is important to examine the conditions of a hot streak in the analysis of gas turbine performance. And most gas turbines will have hot streaks in them. It really just depends on how hot these hot streaks are compared to the average flow. And the better the turbine is designed, the less this difference will be. In general, the turbine blades are fabricated with metals or alloys, and the turbine inlet temperature is higher than the melting temperature of metals alloys, which is usually affected by the pressure. Hence, if the turbine inlet temperature is increased to enhance efficiency, the flow and heat transfer characteristics of the blade surface will be significantly affected. If a suitable cooling method cannot be provided, a sudden increase in heat loads will be produced on the blade surface, which will ultimately reduce the fatigue life of the blade or could even damage the blade after a certain time. Primary turbine blades can suffer several types of damage, such as dents, scores, and scratches, which can occur on the leading as well as the trailing edges of the blade and which have a significant effect on the gas turbine performance. So replacing the damaged blade is more expensive than repairing it. And it's actually really cool how they can make blades. So now technology is really advanced where they're doing 3D printing of blades, but historically they would often make blades what's called out of one crystal. So if you look at a metal, for example, there are things called dislocations in the metal, and this is where the molecules inside the metal they're obviously linked, but sometimes you get defects where these molecules are not linked, and then these are called dislocations, and these are effectively fault lines where the blade can expand along that zone. So you can have a longer blade just by spinning it faster because of centrifugal forces, which produce forces on the blade and expand it through these dislocation lines. And if you have the wall of your cowling or your shroud very close to the blade tip, these tips can actually then start hitting the outside, these shrouds or cowlings, and wear them away or even damage the blades. So that's one way of making a blade out of one crystal, so it doesn't have these dislocations, and that means it won't expand in that same sort of fashion, and then you can have a safer blade. But now with 3D printing, it's pretty cool. They can even print blades quite well. So anyway, let's move on. Primary turbine blades can suffer several types of damage. Oh, we already covered that, sorry. Let's go on to, there's a method to repair these damaged blades in a compressor, for example, i.e. the blending method. And this actually results in the damaged blade becoming smoother, and it increases the aerodynamic performance compared to the unmodified blades. However, this is for compressors and not for turbines, I guess. The difference between a compressor and a turbine is that compressors add energy to the flow, turbines take energy out. That's a very easy way of thinking about it. So if you look at a turbojet, what you have in a turbojet, the anatomy of a turbojet is you have the inlet, then a compressor, then the burning stage, then the turbine, then the outlet. You can have other things such as afterburners and bypass flows to make them turbo fans if you want to, but just a typical turbojet is just those components, And the compressor is there to add energy into the flow to compress the flow. The reason why you want to do that is because you can increase efficiency. And actually, the efficiency of a turbojet is directly proportional to the compression ratio. Then as you burn the fuel or whatever you have, that then adds a lot of energy into the flow, increases the temperature. The enthalpy really dramatically increases through that stage. Then the turbine extracts energy to send back to the compressor to do its job. And that's how the turbojet works. In this particular case, we're just looking at the turbine itself. So that's a little crash course for you. But back to turbines, it is necessary to examine the influence of rotor blade damage on the flow and heat transfer in high-pressure gas turbines under the hot stroke condition. This study provides a clearer understanding of the heat flow and thermal characteristics of gas turbines with blades damaged at different locations. So the blades can be damaged not just at one particular location, but many different locations if you like. And the typical anatomy of a turbine is you have the rotor and the stator, or you might have several stators and several rotors in different stages. So a rotor is like a disc with all these blades coming out of it, and that rotates around. The stator is exactly the same, except it doesn't rotate around. And the reason why you have a stator compared to a rotor is that the rotor, it moves and it takes energy out of the flow. But by doing that, the flow then will change direction. And as the flow goes downstream, you want it to be aligned in a certain way. So the stator behind the rotor aligns the flow so that you can use it more efficiently. So you understand, first of all, what the flow is going to be traveling like, and secondly, directing it to where you want it to go. And often you'll have a stator upstream as well to direct the flow into the rotor in a particular way, so to increase the efficiency of the rotor itself. So you have a stator upstream, then the rotor, then a stator downstream. This study is looking at the effects of dents on the rotor, and then also how those dents on the rotor affect the stator downstream's performance, because obviously you have the downstream influence happening. And not only that, you will also have an upstream influence because if the flow isn't sonic or supersonic inside the turbine, which it won't be, then you have upstream information occurring. So whatever happens downstream will affect upstream a little bit as well. For example, if you increase the back pressure, so the pressure downstream, that will affect how the flow goes over the upstream stator and whether the flow stays attached or not. So if you have a greater pressure pushing back, that can result in premature stall, and then you can reduce the performance of your turbine that way. So they're all connected, and this is also as a function of the outlet as well. If you something called perfectly expand the gas, overexpand or underexpand it. I don't want to cover this too much because it's a whole topic in itself, but just briefly, when you have a gas going through a turbine, it's going to be at a certain pressure. And ideally, you want to have that pressure that's exiting the turbine through the outlet to be the exact same pressure as the ambient. The reason why is because that will mean that you've expanded the flow enough and you've extracted as much energy as you can. Now, if you don't do that, then it's called underexpanded because you haven't expanded it enough. That means that the pressure coming out is higher than the ambient, and then the wake will, or the jet coming out, will expand as you come out. So if you look at the wake coming out of a turbojet, you can actually tell whether it's underexpanded, overexpanded, or perfectly expanded just by looking at the wake. If it dramatically increases in size, then it's underexpanded. If it shrinks, then it's overexpanded because the pressure coming out is less than the outside pressure, and the outside pressure then like compresses that wake. If it stays constant, then it's perfectly expanded, and that means that you've done your job properly with the turbine and the entire turbojet in this case. So moving on to the blades that they looked at. So they have a typical reference blade, and this is the reference blade is pretty much like a NACA 4412, NACA 4412 airfoil, where it's about 12% thickness from what I can tell about that, and it has cambered about the same amount as a 4412. And this is a quintessential airfoil that we look at for airfoil wings on airplanes. Now, along with that reference airfoil, they then have the airfoil again, but they put dents in certain places. So they put a dent on the pressure side and suction side, each one, one on one case, one on the other case, and then they put the dent either near the blade tip or the blade midsection. And they wanted to see how these dents in these different locations affected the performance of the blade and then the data downstream. So moving on to some of the results, they did some CFD on it. I'm not going to cover that because it's just basic stuff. Actually, let's cover the boundary conditions. So the magnitude of the total pressure used for the inlet was 344,000 pascals, and the uniform intensity of 5%. So that's not that high, not that low. It's about normal. A non-uniform temperature, which was considered as the hot streak condition, was applied. The maximum and average temperatures of the hot streak were approximately 839 and 728 Kelvin, respectively. So in other words, the hot streak was about 111 degrees higher than the average temperature of the general flow. The speed of the rotor blade was fixed at 3,600 RPM. Now that's not that much actually. In terms of turbines across all industries, this is actually fairly low. You can get turbines running up to like 100,000 RPM. So 3,600 is not that high. Furthermore, to investigate the effects of rotor blade damage coupled with the hot streak condition, they analyzed 5 different rotor blade cases. As I mentioned, the reference blade, then a dent on the pressure side near the wing tip, then a dent on the suction side near the wing tip, then a dent in the midsection on the suction side, then a dent on the midsection on the pressure side. So the undamaged rotor blade was considered the reference case, and then the other 4 were considered in reference to that. So for the hot streak that they made, they put the hot streak pretty much in the center of the entire flow. So if you look at the flow cross section, the hot streak is just right in the middle. And does this make sense? To some degree, yeah. So on the edges, you have a much cooler flow by about 200 degrees Kelvin. And that kind of makes sense because when you're near the edges, you're near the actual walls of the turbine, and that is going to extract more energy into the material. Whereas when you're in the center, there's only really air around you, which is also hot, when you can't really transfer too much heat. So the heat transfer rate is proportional to the temperature difference. The greater temperature difference, the greater the heat transfer. And it's actually a really cool trick. So if it's a cold day and you go up to someone like your friend or whatever, and you put your hand on their shoulder or arm, if they're cold, then it means either one, they have a really insulated jacket, so the temperature difference between their outside of the jacket and the temperature of the air that they're around is low, so the heat transfer will be very different, very small. So that's one case. The other case is that they're frozen inside so that they don't actually have a very high temperature to begin with, and their jacket isn't doing much, but because they're so cold, the heat transfer is low because the temperature difference is low. So it's one of the two. Either you're really doing well or you're frozen. So it's one or the other. And that's a really cool trick that you can use with your friends. So let's move on to the results. So the flow characteristics, they say that figure 5 shows the velocity streamlines and total pressure contours at different locations on the blade. Let's have a looky look at that. So with the total pressure, one thing that they noted was that at the hub, let's say, so the blade root, they had a less flow circulation zone in the reference case compared to the other cases. However, for the damaged blades, this zone was not present, so this recirculation zone was higher for the undamaged case near the wing root. And this was due to the effects of the altered blade profile on the flow in the spanwise direction. For the mid-span, in comparison with the reference case, the middle damaged cases exhibited more circulation, while the top damaged cases exhibited less circulation. So in other words, at the mid-span, when you had a damaged blade there, then you increase the circulation compared to the reference case. But if the damage was near the wing tip, the circulation would drop compared to the reference case. So as a result, a noticeable difference in the total pressure contours at the mid-span can be seen among the 5 cases. The middle damage cases exhibited lower total pressures than other cases at the mid-span since they had more flow circulation at this location. Moreover, at the wing tip, a lower total pressure can be observed in the top damage cases than the other cases. This is because a small flow circulation was generated in the top damage cases compared to the mid damage cases and the reference case. So it can be concluded that the damage location affected not only the circulation zones at the suction side of the blade, but also the total pressure near the damage. So this is one thing that they found, which was when you damaged the blade, either at the mid-span or at the tip, the pressure side wasn't really affected too much. It was mainly the suction side, regardless of whether the damage was on the pressure side or the suction side. The suction side was usually affected far more in terms of the flow than the pressure side for some reason. They say that the highest temperature on the pressure side of the blade was near the midspan of the leading edge, which exhibited more vorticity and was affected by the hot strip condition. The damage did not affect the temperature distribution on the pressure side, but it significantly affected the temperature distribution on the suction side. So as I mentioned, for some reason, even if you have a damaged pressure side, the suction side gets affected more. So that's quite strange. So as shown in figure 6, let's have a quick look at figure 6. What they have here is the temperature distribution of the blade for the suction side and the surface and the pressure side. And what they found was, so again, the pressure side is not really affected too much in terms of the temperature distribution. They look pretty similar. But the suction side, if you damage it anywhere, the temperature is much higher on that side, especially if you damage it in the midsection. So if you had a little notch at the midsection, for some reason, the high temperature region covers like 3 or 4 times the area as the reference case. So that means that the blade is hotter now. So that's not good for fatigue because typically if you heat metal, it gets weaker. And if you don't quench it properly, it also results in it being weaker after it's cooled down too. So they have figure 7 here, and it gives you the average and maximum temperatures on the blade. And as we mentioned, for all damaged cases, the average and its maximum temperatures are greater than the reference case. But also, as you damage the midsection compared to the top section, the temperatures increase as well. And if you damage it on the suction side compared to the pressure side, the temperatures also increase. So what this means is any damage increases the temperature. If you damage it in the midsection, you increase temperature more. And if you damage it on the suction surface, you increase temperature even more. That's the way it goes. They say overall, the total pressure increased when damage occurred on the blade. The increase in total pressure resulted in an increase in the leakage flow passing through the blade tip or the main passage flow. So this is effectively the wingtip vortex. The attributes of heat transfer are strongly affected by the flow vortex structure. So figure 9, they have some isosurfaces showing the vortex that occurs at the wingtip section. And what they noted was that they actually used a lambda 2 case to determine where these vortices were, which is quite nice. I'm a big fan of lambda 2. They say that in comparison with the reference case, the top damage cases, so the damage near the wingtip, exhibited a weaker tip leakage vortex, while the middle damage cases exhibited a strong tip leakage vortex, which is quite interesting. Like when you think about it, if you damage the tip, the vortex gets weaker. If you damage the midsection, the vortex gets stronger, even though the vortex is much further away from the midsection than at the tip. It's near the tip. So even though you damage the blade very far away from the wingtip, it still affects the wingtip flow. The pressure field directly affected the tip leakage flow conditions, since the tip leakage flow is driven by the pressure difference between the pressure side and the suction side of the rotor blade. And you can see that kind of behind the, like if you look at the blades at the wing, at the trailing edge, you can see that the pressure is a little bit lower for the blades where the tip was damaged compared to the reference case. And then also for the blades where the midsection was damaged, the pressure is a little bit higher, a little bit lower, sorry. So that's what's driving that change in wingtip vortex. So they say that they have figure 10 here, and this shows you the pressure difference between the pressure and the suction sides of the blade and the leakage flow passing through the blade tip under various blade conditions. So let's have a look here. So interestingly, they show that if you have a damage at the tip of the blade, whether it's on the pressure side or the suction side, the pressure difference between the suction and the surface and the pressure side drop compared to the reference case. But if you have damage at the midsection, regardless of where it is, the pressure difference increases. And then this also mimics the tip leakage flow, where if you have a lower pressure difference, tip leakage flow is less because there's less of a pressure difference driving that tip leakage flow, compared to if you have a higher pressure difference, then you have a greater tip leakage flow because there's more of a pressure difference driving that. So the thermal intensity of the flow increased due to changes in the blade profile resulting from the damage. The thermal intensity also depended on the damage location. So damage on the pressure side generated a higher thermal intensity downstream than damage on the suction side did. In addition, damage at the middle created more turbulence than damage at the top. This is because they had applied the hot streak for the inlet conditions with the highest flow at the center, which had a more significant effect on the middle of the blade than at the top of the blade. So they say that due to the effects of damage, the total pressure at the stator downstream, so that it's effectively another blade, but it's downstream as part of the stator, the total pressure increased by 0.25% and 0.5% for the top and for the tip and middle damage cases respectively. The changes in the rotor blade profile affected not only the passage flow, but also the flow on the blade and vane surfaces due to their effects on the total pressure and consequently on the leakage flow through the blade tips and passages. So they say that the structure of the flow strongly affects its characteristics and the heat transfer properties of the vane surface. So now we're going to be looking into the stator, which they're calling the vane. So we looked at the rotor to begin with, but now we're looking at the downstream stator, which I mentioned previously that with turbines, you often have stators upstream and downstream of the rotor to align the flow properly so that you can maximize your efficiency. So now looking at the stator. And this is very important because not only does the entire turbine section work together, where if you change one stator, it's going to change the entire turbine performance. But if you have the turbine in conjunction with other things such as a compressor, that's also going to affect the compressor as well, and also the outlet and inlet and everything. So they're all linked together. And this actually reminds me of a anecdote from when I was doing high school chemistry. So this is as a side note, but it's similar enough that I think it's relevant. So this shows you how important how much things are linked. So when I was doing high school chemistry, my teacher was talking to us about safety for chemistry, and he says when you're mixing chemicals on that and something goes wrong, you usually don't hurt yourself because, like, if something goes wrong, you drop the test tube or something and you're not injured. But what happens is the person next to you will hurt you because they'll throw the test tube away and it'll hit you. They're trying to save themselves, but by doing so, they throw it onto you and you get hurt. Same kind of thing as the rotor and the stator, where they're both connected, and the rotor, whatever it does, is going to affect the stator, and whatever the stator does, it affects the rotor. So I don't know, that's what it triggered in my mind. So I hope you like that little anecdote. Anyway, let's move on. So the temperature contours of the stator blade under various rotor blade conditions are looked at. So for unlike the rotor blade, the damage resulted in significant changes in both the pressure and suction sides of the stator blade. This stator blade received more leakage flow when the rotor blades were damaged. Hence, more flow arrived at the stator. The greater flow produced higher temperatures on both the pressure and suction sides of the stator blade. This led to a significant increase in both the average and maximum temperatures. They said they're showing them in figure 14. So let's have a quick look at figure 14. Okay, so they have just the typical graph, and it shows that regardless of where the damage is on the rotor, the stator had a increase in average and maximum temperatures. They also have pretty cool distributions where they show that like any damage to any of the blades dramatically increases the temperature on the stator blade on the suction surface a lot. Like the on average, I have it here. On average, it increased by like 10 degrees, and then the maximum increased by about the same amount as well. But also on the suction surface, the temperature also increased a lot as well. So the damage on the rotor was no good for the stator at all. So these changes are more noticeable than those for the rotor blades. So the rotor blade is affecting the stator more than the stator is affecting the rotor. The rotor blade is more affecting more the stator than itself in terms of the damage, which comes back to my chemistry anecdote where it's usually the idiot next to you who hurt you, not yourself. So this increment in the temperature of the stator blade surface generated higher thermal stress, which consequently reduced the fatigue life of it. It can be concluded that the damage on the rotor blade had more significant effects downstream than at the blade itself. So let's look at the heat transfer characteristics. The heat flux on the surface side of the blade increased noticeably when the blade was damaged for the rotor. Moreover, the heat flux increased significantly at the edges of the damaged locations. This caused a sudden increase in thermal stress around the damaged locations, which caused the damage to become more critical and reduce the fatigue life of the blade, the rotor blade. Another reason for the sudden increase in heat flux around the midspan was the hot streak applied to the inlet flow. With the hot streak, the highest temperature was centered at the center of the flow. This is because of the conditions that they put on. Coupled with the altered rotor blade profile, it caused a significant increase in the heat flux at the suction side around the midspan location. Overall, when the rotor blade was damaged, the heat flux increased suddenly at the suction side of the blade, the rotor blade, and around the damaged region. Hence, it is necessary to provide a suitable cooling method to prevent these stresses from occurring. So they have a figure of the heat flux distribution on the rotor blade under the different blade conditions. And again, regardless of whether the blade is damaged on the suction side, pressure side, midspan, tip, it always increases the temperature and the heat flux on the suction side. And even a little bit on the pressure side. One thing to note is these damaged regions, they create little notches, and that creates temperature concentration. So the little notches, the edges of them, they are much higher in temperature and heat flux than anywhere else, and that's going to lead to greater fatigue again and wear, and that's going to result in these regions being the weaknesses of this blade. That's where they're going to probably fail. So on the pressure side, the heat flux increased noticeably when the blades were damaged. The high heat flux region extended in the spanwise direction in both the top damage and middle damage cases. This phenomenon occurred due to the increased thermostensity of the flow and the increased vane surface temperature in the damaged blades. The combined effects of the thermostensity and temperature tended to increase the heat flux on the pressure side of the stator blade. Similarly, the heat flux on the suction side increased due to these coupled effects. The high heat flux regions on the pressure side of the stator blade were located around the midspan, while those on the suction side were located near the hub and the tip. Overall, the damaged rotor blade significantly increased the heat flux on the stator blade surface. So again, a massive downstream effect. Hence, to protect the stator blade surface from sudden changes in thermal stresses, efficient cooling is needed as well. So again, like regardless of whether the rotor was damaged at the tip, midspan, suction side, pressure side, the stator blade has an increase in the heat flux both on the suction sides and pressure sides compared to the reference. So now they introduced a really cool number. I didn't know about this number. It's called the Stanton number. They say to analyze the heat transfer at the blade tip under various blade conditions, contours of the Stanton number distribution on the blade tip were plotted. So the Stanton number, what is that? It's in basic words, it's how much heat transfer is being transferred to something compared to how much can be transferred based on its thermal capacity. So in other words, the higher this number, the more heat transfer is occurring. And what they found was that compared with the reference case, the tip damage cases, exhibited lower heat transfer, while the middle damage cases exhibited higher heat transfer. This result is consistent with the pressure difference and tip leakage flows shown earlier, where the middle damage cases exhibited more tip leakage, as well as the results of the previous studies showed the similar sort of thing. In addition, the high heat transfer regions were located at the pressure side of the blade, while the low heat transfer regions were located on the suction side. This occurred because the heat transfer at the blade tip was directly affected by the leakage flow from the pressure side to the suction side of the blade. Tip leakage flow in the tip damage cases was lower than that for the reference case. The high heat transfer regions near the pressure side narrowed, and the low heat transfer region near the suction side widened. On the other hand, the tip leakage flow for the middle damage cases was higher. So that means that the low heat transfer region near the suction sides narrowed, and the high heat transfer regions near the pressure sides expanded. So the heat transfer was really shifted from the suction side to the pressure side. Now, finally, moving on to the aerodynamic and total efficiencies. So looking at the efficiencies of this turbine now, they introduced two different measures, the aerodynamic one and the total efficiency. Both the efficiencies are strongly dependent on the damage locations and exhibit the same trends. Compared with reference cases, the tip damage cases, exhibited a slight increase in efficiency. However, the middle damage cases exhibited a slight decrease in efficiency. So compared with the reference case, the middle damage cases exhibited a significant increase in drag force, while the tip damage cases exhibited a reduction in the drag force. On the other hand, the middle damage cases had a lower lift, whereas the top damage cases had a higher lift. So overall, the tip damage cases were better overall, where the drag reduction and the lift increase. So the changes in the drag and lift forces can be explained by the velocity contours, as we mentioned earlier, where they change the circulation around the blade. In the middle damage cases, the circulation zone on the suction side was closer to the leading edge at the midspan than in the other cases. This means that the flow separation point in the middle damage cases was closer to the leading edge than in the other cases. According to flight theory, the closer the separation point moves to the leading edge, the higher the drag and the lower the lift generated. So in other words, the closer the separation point to the leading edge, more the blade will be in separation, which means it's not going to be doing much. Now, there are some times where this isn't the case, but generally speaking, this is the case. On the other hand, for the tip damage cases, the separation point was farther away from the leading edge than the reference case. So that means that more of the wing or more of the blade is producing lift and reducing drag. There's less separation flow over it. So that's why you're getting this beneficial result. So as a result, the aerodynamic efficiency increased slightly for the tip damage cases, but reduced slightly for the middle damage cases. So if the blades are damaged, the damaged locations significantly affect the turbine efficiency. Specifically, if the top part of the blade is damaged, the turbine efficiency can be slightly increased or modified. So in other words, the damage is actually pretty beneficial for the turbine, except that it will reduce its lifespan. But before then, it would be pretty good. And it plotted the drag and lift forces compared to where the damage was. And as I mentioned, if you damage the blade on the pressure side near the tip, you get a massive reduction in drag, about 4%. But if you damage it on the suction side, the drag doesn't really change too much compared to the reference case. And similarly, if you damage it on the midsection at the suction side, the drag doesn't change too much either. But if you damage it on the pressure side, the drag increases slightly. So what this means is there are only certain configurations where the drag will be reduced. On the other hand, for the lift, if you damage it at the tip, regardless of whether it's for the pressure side or the suction side, the lift will increase quite a bit, about 2% or 1%, regardless. However, even if you damage the blade at the midsection on the pressure side, the lift is increased a little bit still, so that's pretty decent. But if you damage it on the suction side, lift, no dice, the lift is dramatically dropped. So that's an interesting relationship there. So in conclusion, before we get to that, actually, I want to just plug our instrument, the Atmosphere Hawk. It accurately measures the density of air in your wind tunnel. And the reason why you need to do this is because the density of air changes by about 2 to 4% every day. And it changes more between days and between weeks and months and seasons. So if in your wind tunnel, you're not keeping track of the temperature, pressure, and humidity, the air density is going to be changing, and that's going to introduce errors about 2 to 4% in your results. That affects even the most basic stuff from the free stream velocity and Reynolds number to more complex stuff such as vortex shedding and stall patterns and intensity, how that affects the flow and everything. So you need to keep track of their density. Atmosphere Hawk, it's an instrument that makes it very easy for you to do. It plugs in straight into power and it works out of the box. So get one to make your experiments easier and better. Link in the description. Okay, so let's move on to the conclusion. So from this study on how the blades being damaged affect the aerodynamics and the heat transfer of the blades, they say that the average and maximum temperatures on the rotor blades and the stator blades surfaces of the damaged blades were higher than those in the reference cases. This was due to the effects of the altered flow fields on the damaged blades. The tip leakage flow increased in the middle damaged cases, but decreased in the tip damaged cases compared to the reference case. The heat transfer on the blade tip in the middle damaged cases was remarkably higher than the one in the other cases. The location of the damage had significant effects on the heat transfer characteristics of the rotor blades and stator surfaces. On the rotor blades, the heat flux around the damaged location exhibited a sudden increase. The heat flux on the stator blades surface considerably increased around the mid-span on the pressure side and around the hub and the tip on the suction side. This led to an increase in the local thermal stress, showing a potential reduction in the fatigue life of the blade and the vane, on the rotor blade and the stator blade, which would increase the maintenance costs. Finally, the modifications to the tip damaged blades enhanced aerodynamic and total efficiencies, while the same for the middle damaged blades caused reductions in the efficiencies. So that's in this podcast. Make sure to like, subscribe, and check out Atmosphere Hawk. And make sure to check out other podcasts to get more knowledge in your brain. And I'll see you next podcast. Peace out, amigos.